Transient Processes in Linear Circuits. Hello everyone, welcome to my channel. My name is Rafael, I'm an electrical engineer, and in this video I would like to invite you to debate with me transient processes in linear circuits through 8 exercises that frequently appear in exams for electrical engineers. Let's go to the first exercise. If the switch in the circuit has been open for a long time and there is no energy stored in the inductor, what is the magnitude of the current 60 microseconds after the switch is closed? Okay, my friends, this is the exercise. Let's go to the solution. As there is an inductor in the circuit, its characteristics will determine circuit behavior. Okay? For an inductor, VL of t is equal to L times the derivative with respect to time of I of t. Okay? The source is DC, and there will be voltage across the inductor only when the current is varying. Okay? In steady state, the current does not vary anymore. Therefore, after a long time, the inductor will behave as a short circuit. The exercise wanted us to calculate the magnitude of the current 60 microseconds after the switch is closed. After the switch is closed, we have that V is equal to VR of t plus VL of t. This voltage is equal to the voltage of the power supply, 10 volts. Let's forget the number and work with V. V is equal to R times I of t plus L times the derivative with respect to time of the current. This is the differential equation that we are going to work on. It has one homogeneous solution and one particular solution. To calculate the homogeneous solution, we are going to set the forcing term to 0. Okay? The homogeneous solution is of the sort k times e raised to the power of RT. And we are going to apply this solution to the differential equation, but when V is equal to 0, and we find that if we take the derivative, we get that and from this step, we find that R is equal to minus R over L. Okay? This enables us to find the homogeneous solution. Now let's work on the particular solution. The particular solution has to reflect the nature of the forcing term. The forcing term is DC. Then the particular solution will be a constant. This is the homogeneous solution, and the particular solution will be a constant. Okay? And we are going to apply this here, alright, without setting it to 0. It is going to be 10 volts. And we find that V is equal to R times A plus L times the derivative with respect to time of a constant. We know that the derivative of a constant is 0. Consequently, A is equal to V over R. With these results, we can find our general solution. Our general solution to the differential equation is I of t equal to k times e raised to the power of minus r over L times t plus v over r. Okay, this is the general solution. But since the exercise stated that at t equal to 0, at t equal to 0 plus the current is 0, this was stated by the exercise, we set it here to 0. I of t equal to 0 plus is equal to k. Every number raised to the power of 0 is 1 plus v over r equal to 0. Then we find that k is equal to negative v over r. Alright? With these results, we find the circuit's current for all t greater than 0. I of t is equal to v over r times 1 minus e raised to the power of minus r over L times t. This is the general solution with both parts, the homogeneous solution and the particular solution. To finish, we need to use the values. The exercise wanted us to calculate the current for 60 microseconds. And in this way, negative r over L times t will be equal to negative 2 times 10 cubic ohms, 60 times 10 to the negative 6 seconds, and the inductance is 80 millihenry times 10 to the negative 3 Henry, which is negative 1.5. V over R is equal to 10 volts over 2 kilo ohms, and this is 5 milliamperes. We have all the parameters, and ultimately I of t equals to 60 microseconds will be equal to 5 milliamps times 1 minus e raised to the power of minus 1.5, which is equal to 3.88 milliamps. This is the magnitude of the current after a time of 60 microseconds. Okay, my friends, this is all for exercise 1. Let's go to exercise 2. Question number 2. The switch in the circuit has been open for a long time and there is no initial charge on the capacitor. If the switch is closed at t equal to 0, what is the steady state voltage across the capacitor for t greater than 0? Okay, my friends, this is the question. Let's go to the solution. Observe that the voltage here is DC. Okay? It is a DC power supply. What does it mean? It means that the voltage across all elements will be DC as well. And as the source is DC, in steady state, the capacitor behaves as an open circuit. Pay attention to this. Okay. What is that? What does it mean? This is the expression of current through a capacitor. Observe that there is current only when the voltage is varying. If the voltage is constant, DC, then the derivative of a constant is 0, then the current is 0. Alright? If the current is 0, the capacitor is behaving as an open circuit. Okay? Then, if the capacitor is behaving as an open circuit, the current here is 0 amperes. There is going to be current only here. Okay? Consequently, we can find the voltage here on this resistor here. And this voltage will be the voltage across the capacitor. Vc will be 40 volts times 2 kilo ohms divided by 2 kilo ohms plus 2 kilo ohms. We apply the voltage divider rule here, and we find that the voltage across the capacitor in DC, in steady state, is 20 volts. Okay, my friends? This is all for exercise 2. Let's go to exercise 3. Exercise 3. The exponentially decaying voltage given is applied to a digital circuit input. V of t is equal to VO times e raised to the power of negative t over tau, in which VO is 20 volts and the time constant of the circuit is 400 milliseconds. If the digital circuit triggered voltage is 20 volts, what is the time needed for the decaying voltage to reach the trigger voltage? Okay, my friends, that's the question. Let's go to the solution. V of t has to reach 2 volts for triggering, but the initial value of the voltage is 20 volts. It's going to take some time. Let's calculate this time. 2 volts, which is the voltage for triggering, has to be equal to 20 times e raised to the power of negative 3 divided by 400 milliseconds, which is 0.4 seconds. Dividing 2 by 20, we find 0.1 equal to e raised to the power of negative t over 0.4. Taking the natural logarithm, we find that ln 0.1 is equal to ln e raised to the power of negative t over 0.4. Negative 2.3026 is equal to negative t over 0.4. And ultimately we find that the time it takes for the decaying voltage to reach 2 volts is 0.92 seconds. Okay? This is the time it takes to go from 20 volts to 2 volts. Alright, my friends, this is all for exercise 3. Let's go to exercise 4. Question 4 now. The switch in the circuit has been open for a long time and there is no initial charge on the capacitor. If the switch is closed at t equal to 0, how long does it take for the capacitor voltage to reach 80% of the battery voltage? Okay, my friends, this is the exercise. Let's go to the solution. If the switch is closed, V is equal to VR of t plus Vc of t. Okay? For a capacitor, we know that I of t is equal to C times the derivative with respect to time of the voltage. As there is a capacitor in the circuit, its characteristics will determine current behavior. Then we are going to describe the current in terms of the characteristics of the capacitor. We know that for a resistor, VR of t is equal to R times the current. Okay? This is the voltage across a resistor. And we are going to use this expression here, okay? Then it becomes V is going to be equal to RC times the derivative with respect to time of I of t of Vc of t plus Vc of t. Alright? This is the differential equation that we need to solve to calculate what the exercise wants us to calculate. And the general solution of this differential equation has one homogeneous part and one particular part. Let's work on the homogeneous solution first. The homogeneous solution is going to be of the sort VCH of t will be equal to K times C raised to the power of RT. If we apply this to the differential equation, but bearing in mind that for the homogeneous solution, the forcing term is set to 0, okay? Then it is going to be 0 equal to RC times the derivative with respect to time of ER of t plus ER raised to the power E raised to the power of RT. And from this we get that R is equal to minus 1 over RC. Okay? Now let's work on the particular solution. The particular solution has to reflect the nature of the forcing term. The forcing term is a DC power supply. Then the particular solution is going to be a constant. VCP of t is equal to A. We apply this to the expression, okay? V is equal to RC times the derivative with respect to time of A plus A. The derivative of a constant is 0, then A is simply equal to V. And from these results, we get our general solution. Vc of t is equal to K times e raised to the power of negative t over RC plus V. And since the exercise stated that the voltage across the capacitor is initially 0, okay, Vc over t equal to 0 plus is equal to V to 0 volts. And as we know that the voltage across a capacitor does not change immediately, we can confidently say that we set this to 0, okay? We set this to 0 for t equal to 0. Any number raised to the power of 0 is 1. Then k plus v is equal to 0, where k is equal to negative v. And thus, for t greater than 0, we have that Vc of t is equal to V 1 minus e raised to the power of negative t over Rc. Okay, this is the solution of the differential equation. But this is not the end. The exercise wanted us to calculate the value of the voltage across the capacitor when it is, let me refresh my mind here. If the switch is closed at t equal to 0, how long does it take? So we are going to calculate the time. How long does it take for the capacitor voltage to reach 80% of the battery voltage? This is what the exercise wants us to calculate. The time it takes. Okay, so the exercise wants us to calculate the time it takes for the capacitor voltage to reach 80% of 20 volts. 80% of 20 volts is going to be equal to 20 1 minus e raised to the power of t over Rc. If you calculate Rc, substituting these values here, you're going to find 15 milliseconds. Okay, then we use 15 milliseconds here. %80 of 20 volts is 16. 16 volts is equal to 21 minus e raised to the power of negative t over 15 milliseconds. Okay? We are going to manipulate this and find that 0.2 is equal to e 0.015. You can use the natural logarithm on both sides, and ultimately you find that t is equal to 24 milliseconds. This is the time it takes for the capacitor voltage to reach 80% of the voltage of the battery. Okay, my friends, this is all for exercise 4. Let's go to exercise 5. Question 5. Determine the time constant of the circuit. Let's solve it. To calculate the time constant, we may simplify the circuit using Thevenin's equivalent. Okay? This is a possible solution that I'm going to present to you. We are going to use Thevenin's equivalent circuit. Alright? Thevenin's equivalent circuit is composed of the open circuit voltage and the equivalent resistance. Let's calculate the open circuit voltage first. We can immediately calculate the open circuit voltage by applying the voltage divider. Okay? As there is no current here, this voltage here will appear here on top of this resistor here. Applying the voltage divider, we find 0.5 volts. This is the open circuit voltage. To calculate the equivalent resistance, we set the voltage source at rest. Voltage source at rest is a short circuit. The equivalent resistance is going to be the parallel connection between these two resistors here plus this resistor here that will appear in series. And you may try it yourself and find 2 ohms. Okay? Combining these two results here, we find the Thevenin's equivalent circuit as here we don't use the voltage given, here we use the open circuit voltage that we calculated for the Thevenin's equivalent circuit, okay? It is going to be here 0.5. And here the equivalent resistance, and here the inductance. From exercise number 1, we know that if you go back to exercise number 1, we know that I of t, this current here, I of t is equal to V over R times 1 minus e raised to the power of R over L times t. Okay? The time constant of the circuit is L over R. Okay, in this case here, L over R equivalent. If you are participating in an exam and you don't have time to do all this, you can simply memorize this, that the time constant is going to be the inductance divided by the equivalent resistance. If there are many resistances, you can simply jump to this conclusion here. And you're going to find that it is 1 Henry divided by 2 ohms, and this is 0.5 seconds. Okay, my friends, this is the solution of exercise 5. Let's go to exercise 6. Question 6. For the circuit shown in the figure, the switch has been kept closed for a long time and is opened at t equal to 0. Determine IL of 0 plus, V of 0 plus, and IL of t for all t greater than 0. Okay, this is what the exercise wants us to do. All right? Observe that in steady state, before the switch is opened, the inductor is behaving as a short circuit. Okay? How do we know it? We know that VL of t is equal to I times the derivative with respect to time of I of t. In steady state, as the power supply here is DC, in steady state, the current through the inductor does not vary. It is constant. And the derivative of a constant with respect to time is 0. It means that the voltage across the inductor is 0. It is behaving as a short circuit. Okay? That's the conclusion. In steady state, before the switch is opened, the inductor is behaving as a short circuit. Then we know that the VL of 0 minus is equal to 0 volts. The voltage V across the 40 ohms resistor is the voltage of the battery, is equal to the voltage of the battery before the switch is open. Okay, before the switch is open, you see that this voltage is applied here. Then they are equal. This voltage appears here. So V is equal to 24 volts before the switch is opened. And the inductor current in steady state before the switch is open is (24 volts divided by 10 ohms. Which is 2.4 amps. Now, what the exercise wanted, after the switch is opened, thus isolating the source from the circuit, okay, the switch isolates the source from the circuit. The energy stored in the inductor will flow through the resistors, okay? if we isolate the source from the circuit, what is going to happen? What will happen is that the current stored here will flow, okay, through the resistors. And we are going to have a situation like this, without the source. And current will flow from the inductor to the resistors. Okay? Let's combine these two together here. Okay, 40 and 10. Let's combine them and call it the equivalent resistance. The equivalent resistance is going to be 50 ohms. And we are going to have a new situation, and the situation is going to be this. Here is 50 and here 5 Henry. Okay, and the current. This circuit's equation is 50 times I of t plus 5 times the derivative with respect to time of I of t equal to 0. Okay? And if we solve this, okay, if we solve this as we did before, we find that I of t is equal to 2.4 times e raised to the power of negative 10t. Okay? Because this is the initial value of the current, and it is going to decrease exponentially like this. Where the time constant is, okay, this is of the sort I0, the initial value of the current, times e raised to the power negative t over tau. Where this tau is equal to L over the equivalent resistance. The equivalent resistance is 50 and L is 5. We find the 0.1 seconds. And the inverse of 0.1 is 10. That's why the equation governing current behavior is this. We have to consider the initial value of the current and how it decays. Okay, and what did the exercise want? The exercise wanted us to determine this. Okay, this is what we need to determine. The initial value of the current is 2.4 amps. The value of V, now we're going to calculate the value of, we already know this here as well. We already know this here. This is this. 2.4 times e raised to the power of negative 10t. What we need to calculate is only V of t. V of t equal to 0 plus is equal to 40 ohms times the initial current. The initial current immediately after the switch is open. The current that's going to pass here is this one, but in the opposite direction, okay? Because here before the switch is open, the current flows in this way, in this direction here, downwards. Okay? After the switch is open, the current is flowing upwards here. Alright? Then the voltage drop will not point upwards, will point downwards. And this gives a value of negative 96 volts. Okay? And this is all the exercise wanted of us. Let's work on exercise 7 now. Question number 7. For the circuit of the figure, the switch was kept closed for a long time before being opened at t equal to 0. Determine Vc of 0 plus, I of 0 plus, and Vc of t equal to 2 milliseconds. Okay, my friends, that's the exercise. Let's go to the solution. In steady state, before the switch is opened, the capacitor behaves as an open circuit. We have already debated this. The capacitor is behaving as an open circuit. Just to refresh your mind, for a capacitor, IC of t is equal to C times the derivative with respect to time of the voltage. Okay? As the power supply is DC, okay, after a long time, the voltage here will be constant. Okay? Will be constant. The derivative of a constant is 0. This means that the current is 0. When the current is 0, it means that the capacitor is behaving as an open circuit. Alright? The capacitor is behaving as an open circuit. In this way, the voltage across the capacitor is going to be equal to the voltage here. Okay? This voltage here will appear here. They will be the same because there is no current. We simply apply the voltage divider rule and we find that Vc of 0 minus is equal to 2 kilo ohms over 2 kilo ohms plus 500 ohms, okay, times the voltage of the power supply, and this is 40 volts. This is the initial voltage of the capacitor just before the switch is opened. And as we know that the voltage across the capacitor does not change immediately, at t equal to 0 plus, the capacitor voltage will still be 40 volts. For it does not change immediately. Then this is 40 volts. We have already found our first result. Now let's calculate the rest. Else, at t equal to 0 plus, after the switch is open, okay, now let's work on after the switch is open. We're gonna have it open here, okay. The switch is going to open, and the switch is going to isolate this part of the circuit from this part of the circuit. No current, no current is going to flow from this part to this part. But at t equal to 0 plus, by opening the switch, we isolate the source from the circuit. Under these circumstances, the capacitor discharges through the resistor. Okay, the capacitor is going to discharge. The capacitor is going to discharge through the resistors. Initially, I of t equal to 0 plus will be simply the initial voltage across the capacitor, which is 40 volts, divided by 2.5 kilo ohms. And this is 16 milliamps. This is the initial value of the current. This is this result here, 16 milliamps. Okay? For t greater than 0, we know that Vc of t over 2.5 kilo ohms. We are working on the equivalent circuit here, okay? A circuit of the sort. This is 2.5 kilo ohms, and this is the capacitor, okay? 1 microfarad. This plus 1 microfarad times the derivative with respect to time of Vc of t has to be equal to 0. There is no forcing term, then it has to be equal to 0. And from this, we find that if we solve like we did before, we find that Vc of t is equal to 40, the initial value of the voltage, times e raised to the power of negative t over Rc, where in which Rc is equal to 2.5 times 10 to the negative 3 seconds. Okay? This is the time constant of the circuit. We want the voltage across the capacitor at t equal to 2 milliseconds. And we simply apply 2 milliseconds here, using that Rc is this, okay? It is 40 times e raised to the power negative 2 milliseconds divided by 2.5 milliseconds. And this is 18 volts approximately. Okay, my friends? Did you understand what I did? Alright, this is all for exercise 7. Let's go to the last. Let's go to exercise 8. To finish our debate, let's talk about transient in AC. Exercise number 8, find the I of t for t equal to 0, Vc of t, and I of t for t greater than 0 after the switch is closed, assuming no initial charge on the capacitor. Okay? Pay attention that we were working with DC sources. Now we are working with an alternating current source. And we want to analyze what happens when the forcing term is alternating and when there is a switch in the circuit. Okay? The exercises say that the power supply is 2 sine 200t, and the resistance of the resistor is 5 kilo ohms, and the capacitance of the capacitor 1 microfarad. Alright, this is the exercise. Let's go to the solution. At t equal to 0 plus, the voltage of the power supply will be 2 times the sine of 200 times 0, okay? At t equal to 0, 2 times the sine of 200 times 0. And this is 0 volts, okay? Pay attention here that we are considering that the switch is going to close at precisely the same time the voltage of the power supply passes through 0, okay? 0 here means 0 here too, okay, and vice versa. Consequently, I of t equal to 0 plus is going to be equal to 0 amperes, because if the forcing term is 0, then the current is 0 too. Alright, now let's see what happens for t greater than 0. For t greater than 0, the voltage of the source is equal to the voltage drop across the resistor plus the voltage drop across the capacitor. And as there is a capacitor in the circuit, its characteristics will determine current behavior. Okay, then we are going to describe the current based on the characteristics of the capacitor. V of t is going to be equal to RC times the derivative with respect to time of Vc of t plus Vc of t. Okay, this is the differential equation that we are going to work on. And the general solution of this differential equation has a homogeneous part and a particular part. The homogeneous solution is of the sort Vch of t is equal to k e raised to the power of RT. When we apply this to the differential equation, bearing in mind that for the homogeneous solution the forcing term is 0, we find that R is equal to negative 1 over RC. Okay? This is the homogeneous solution. The particular solution has to reflect the nature of the forcing term. Okay? The particular solution has to reflect the nature of the forcing term. Here, the forcing term is sinusoidal. It is not DC. The forcing term is sinusoidal. Then, we have to model the circuit. Our particular solution has to reflect the nature of the forcing term. Then, our particular solution is going to be of the sort okay, this is going to be our particular solution where A and B are constants. We need to find their values. W, we already know, W is 200. Okay? How do we find A and B? We need to apply this to the differential equation that we discovered. Okay? And applying this to the differential equation and making it equal to the forcing term, we get that RC times the derivative with respect to time of A times the sine of Wt plus B times the cosine, here is cosine, okay? Times the cosine of Wt plus A times the sine of Wt plus B times the cosine of Wt, 2 times the sine 200t, okay? Observe that our differential equation has a differential here, okay? Then the derivative of sine is cosine, and the derivative of cosine is sine, okay? The derivative of sine is cosine, the derivative of cosine is minus sine. Then, to fully reflect the forcing term, we need to have terms in sine and cosine, okay? I had written here a times sine wt and repeated the sine, but no. It is a times sine wt plus b times the cosine wt, okay? Because one is the derivative of the other, okay? The derivative of sine is cosine, the derivative of cosine is minus sine. Using both sine and cosine, we fully reflect the nature of the forcing term, okay? That's why we do this in this way. And if we take the derivative of this term and add to this, we find that A is equal to 2 divided by 1 plus r squared c squared w squared, and b is equal to minus 2rcw divided by 1 plus r squared c squared w squared. And if we substitute these values here, r, c, and w, we find that a is equal to 1 and b is equal to negative 1, okay? In this way, our differential equation has the general solution of the sort our general solution is going to be Vc of t equal to k times e raised to the power of negative t over rc plus sine wt minus cosine wt. Alright? This is the general solution of our differential equation. RC will be equal to 5 kilo ohms times 1 microfarad, and this is 5 milliseconds. Okay? And ultimately, our differential equation is this. We substitute here. Oh, and let's work on this here. T over RC will be equal to negative 200t, okay? Because the inverse of this is this. Alright. But we still have to find the k. As it was stated that there was no initial charge in the capacitor, we know that Vc has to be equal to 0 for t equal to 0, okay? Vc of t equal to 0 plus has to be equal to 0. If we put 0 here, sine 0 is 0. The cosine of 0 is negative 1. Then it is going to be k minus 1 equal to 0. And we find that k is equal to 1. Alright? In this way, our differential equation will have this general solution here. The solution of the differential equation is Okay, this is the general solution of the differential equation with both parts, the homogeneous solution and the particular solution. To finish, from the capacitor voltage we find the current. Okay, we already found this. Okay, this we already found. This we already found. It is okay. We already found. Now we need to find the current. To find the current, we simply differentiate this. We know that for the capacitor, I of t is equal to c times the derivative with respect to time of the capacitor voltage. And if we differentiate this expression here, using that the capacitance is 1 microfarad, we find that the current is equal to 200 microamperes times E raised to the power of negative 200t plus cosine 200t plus sine 200t. Okay? These are the solutions that we were looking for. This is the general solution of the differential equation that we were working on. And from this solution, we find the current, knowing that for a capacitor, the current is the derivative of the voltage. You can simply try it yourself, differentiate this expression, and I invite you to try to find this. You're going to find this for the current. Alright, my friends, this is the video that I wanted to make, debating transients in linear circuits. I am a teacher. If you want to book a lesson with me, please use my WhatsApp number, guys. Goodbye!